this is the 15.5 video. It is on surfaces and area. So they talk about here in this section that kind of here's what we've done, here's where we're going. And so we've done parametric before. This one's, for whatever reason, only two-dimensional, but they can be three-dimensional with a plus h of t in the k direction on there also. But what's going to be different about what we're going to do now is we're going to do parametric, but this parametric was a function of one variable. Notice it was just a function of t. And now we're going to do them where they're functions of two variables. So now they're going to look like this, and they're going to be functions of two variables, usually u and v, but sometimes something else. So they can be, or they'll be three-dimensional typically, I think in this section. They're all three-dimensional? I'm not sure. But anyway, but they'll be functions of two variables. And so you've got in the I direction a function of u and v, the j direction a function of u and v, and in the k direction a function of u and v. So instead of just t's, now it's u's and v's. And so the u's and v's are called parameters. It's on the uv plane, and then here would be in the x and the y and the z, the components. Okay, so on page 871, they show you how to find the derivatives of these. And so since r is a function of u and v, if you're going to take the derivative of r, you have to do the partial derivatives, and there's two of them. So this is the partial derivative with respect to u, and this is the partial derivative with respect to v. And so notice you're just taking the derivatives of each of the component functions with respect to either u or v. And then on page 872, they have the area of a surface, and it's the same r that you see. And notice the bounds. U is between A and B, and V is between C and D. So they have it written here with U first, but you could also do it with V first. But the area would be the cross product. Well, it's the magnitude of the cross product of the derivative vectors. And so R sub U and R sub V each are vectors. And then when you do the cross product, that's a vector. But then you compute the magnitude, and so that would be obviously not a vector. Okay, and then last formula, page 873. I have it written a little bit better in my notes, so I'll show it to you there in a second. Actually, there's one more formula after this, I think. Yeah, there's one more after this. Okay, anyway, just kidding. So it's not the last one. There's two surface area formulas. So surface area is the last concept, but there's another way to do surface area. So this one would be for if you're able to find the parameterization for the the R, if you're able to find the R, then you can use this one. And so it would be basically just that you're, well, I'll show it to you in a second. It's the same formula, basically. You're just integrating this. I'll show it to you in my notes in a second. But sometimes you can't find the parametric equations. And so in that case, you're going to define it implicitly. Sorry, my daughter. Despite the fact that there's a note on the door saying, I'm making a video, please don't come in. My daughter decided to come in. You gotta love kids. Okay, anyway, sometimes you can't define it in terms of parametric, and so you are going to use this method instead. So I'm not going to read all this to you. This is page 875. There's information here, and there's information here, but basically what it is, you have the surface, and that's the S, and then you have the shadow. It's really the projection, but it's easier maybe to think about it as a shadow. But this would be the projection of the surface. And then you're going to have some vector P. And the vector P, there's two characteristics of the vector P. So the vector P, number one, has to be a unit vector. So P has to be a unit vector, which means it's length 1. And then also P has to be normal to the region. And so normal for a vector is the same thing as orthogonal or perpendicular here. So it's normal to the region, okay? And so that's the two things that this vector P has to have. P has to be a unit vector and be normal to the region. So they talk about some more information here, but basically it boils down to just this. The formula for implicit surfaces as opposed to parametric ones, you have the gradient. Oh, I didn't show you what F was. Sorry. F is just where you have some function of x, y, and z equal to some constant. So C is a number. Over here would be x, y, and z, so it's the stuff on the left. That's what F is. So it's the gradient of F, and then you take the magnitude of it. And then you have the gradient of F dotted into your P, which is, of course, a scalar, not a vector. And so these bars are not magnitude bars. These bars are absolute value bars. So here, these bars are magnitude because the gradient is a vector. These bars are absolute value because this is a scalar since it's the dot product. Okay, so for your P, I don't know where they talk about. I don't know where they talk about it here, but somewhere in this sentence. But if your region is in the xy plane, then your normal vector P would be K, because the vector K is orthogonal, or I mean normal to the xy plane. And then here, if you're in the xz plane, you're going to use J. And if you're in the yz plane, you're going to use I. And so that's what you're going to use for your P vectors, because I, J, and K are unit vectors, and then they're normal to the 3 coordinate planes. Okay, so that's all the formulas. I'm going to show it to you in my notes. So you have here's the new parametric form with the 2 variables. Here's the bounds on the variables. It doesn't matter which one's A and B and which one's C and D. Just know that one of them's one and one of them's the other. You don't have to memorize that. But I wrote these with the subscripts, the F's, F sub U, F sub V, stuff like that, instead of the curly D's, just because it takes up less room this way. So this is just a different way than the book wrote it. The book used the curly D's. And then for area, this is what I was talking about a minute ago. You can do the DU or the DV. So this is just generically over the region R, the A, or you can do here the U first or the V first. So all 3 of these are just the same thing. So if you were going to write the formula for area, you would just pick one of these 3. Don't do all 3. And then surface area, first of all, this letter is sigma, but it's lowercase. You're probably used to capital sigma, and capital sigma is the one we use for like Riemann sums. You used it in series back in Cal B, but this is lowercase sigma. And so it is, notice the same formula for area, because when you're doing area, you're doing the area of a surface, and so surface area. But that's only if you can find the parametric equations for it. If you can't find the parametric equations for it, then you use this bottom formula. So again, the top bars are magnitude, the bottom bars are absolute value. Your F comes from a function of x, y, and z equal to a number. R is the shadow of S, so R is a region, which is 2-dimensional. S is a surface, which is 3-dimensional. P, again, is a unit vector that's normal to R. And then sometimes you use K, sometimes you use I, and sometimes you use J. So that's all the notes. So let's look at some examples. So we're going to start with number 2. Number 2, I guess it's helpful if I read the directions. Page 878. Find a parameterization of the surface. So when you do a parameterization, you have to have the function, but then you also have to have the bounds, okay? So, or the restrictions on the variables, however you want to think about it. So here is my surface. Notice this is, I didn't draw it, but it's a paraboloid. As z equals 9 and then opening down, so paraboloid, but then it stops when you hit the xy plane because z is positive. So we're going to use cylindrical coordinates. Cylindrical coordinates are very common here. I'll show you in an example in a minute how you would know when you can't use cylindrical coordinates, but that's probably going to be your first guess, is cylindrical coordinates, because that's very common. So in cylindrical coordinates, x is r cosine theta, y is r sine theta, and then the z, here's what the z is, but that's not in cylindrical coordinates because x's and y's are rectangular, not cylindrical, so you've got to change it. So you factor out the negative, and then x squared plus y squared is r squared, so z is this, 9 minus r squared. But then from up here, we also know that z is positive. So if z is positive and z is this, then this would have to be positive. And then if you solve for r, you get that r is less than or equal to 3. And then the theta, unless they restrict it to like, first octant or top half or right side or something like that, unless they restrict it, your theta is just by default going to be between 0 and 2 pi. So if there's no restrictions, then it's just 0 to 2 pi. All right, so here's my 2 parameters instead of u and v. My 2 parameters are r and theta. And so this is r, the vector of r and theta, the parameters. These are different r's. So here's the x, here's the y, here's the z. And then again, you have to also include the restrictions on the parameters. And so r is between 0 and 3. Theta is between 0 and 2 pi. Make sure to put those on there. If you don't put those on there, you will lose points because you're not giving all of the information that is necessary. All right, so try this one by yourself. This is number 4. It's also cylindrical, so pause the video and try this by yourself. Okay, so you should have started with the x equals r cosine theta, y equals r sine theta, and then the z, you got to put it in cylindrical also, so x squared plus y squared is r squared. It's under the square root, so z is 2r. And then for the z equals 2 and the z equals 4, if z equals 2 and z is 2r, then r would have to be 1. And if z equals 4 and z is 2r, then r would have to be 2. And so your bounds on your r are 1 to 2. No restriction on the theta, so it's 0 to 2 pi. So you should have your r as a vector. Make sure to put hats on your vector. If you don't put hats on your vector, I'm going to take off points every single time. So put hats on your vector. Vectors, hats on your vectors. Okay, and then here's your bounds. R is between 1 and 2. Theta is between 0 and 2 pi. All right, so I'm going to show you now where an example of one where you cannot use cylindrical. So if you look at this one, the picture's on the next page. I'll tell you it here and then I'll show you the picture. So this is a sphere centered at the origin, radius square root of 8. And then you're cutting it by this plane z equals -2. So the plane z equals -2 is parallel to the xy plane, but it's 2 units below it. So my picture's not really good. There's the sphere, and then you come at the bottom of the sphere and cut it off with a plane. So here, so it's like flat right there. I can't think of anything that looks like that in real life. I don't know, but it's a little flat circular piece on the bottom, flat circular piece there, where the plane cut it off. And then it said in the problem that it's the upper part, so it's this part up here instead of this little part that's missing. So there's a little part right here that's missing. So it's not that, since it said the upper part. It's everything above this plane z equals -2. Okay, so let's pretend like you didn't know you couldn't use cylindrical here, and you tried. So if you tried, you want to solve this for z. So move this stuff over. But then when you go to take the square root of both sides, because the z is, if you look at my picture, here, this circle was radius square root of 8. Square root of 8 is the same thing as 2 square roots of 2. So the radius could be, in terms of the z, it could be all the way up here at 2 square roots of 2, or it could be all the way down here at -2. So your z is between -2 and 2 square roots of 2. So you'd have to have the plus or minus, because sometimes z is positive and sometimes z is negative. And so if you have the plus or minus, then you have 2 different functions for z. You can't have 2 different functions for z. You have to have just one function. And so that's how you know you can't use cylindrical. So if you get something like that where it would have a plus or minus in it, then it's not okay to use cylindrical. So we're going to use spherical. So these formulas were on page 810. Page 810 is where the formulas are. And so you can look them up if you forgot them. But here's x and y in spherical. And then this was what they gave me in the problem. And so x squared plus y squared plus z squared is rho squared. And so solving for rho, I get the 2 square roots of 2. And so you can take that, since rho is always that, you can take that and plug it in here and here for rho. So x is now 2 square roots of 2 times this, and y is that. So now if you look at the z, this again is from page 810. Z is this. Rho is 2 square roots of 2. So z becomes this. But then they told me back here in the problem that z was also -2. And so if z is -2, you can set those two equal to each other, divide both sides, and you get cosine of theta. It's not theta, that's phi. Cosine of phi is -1 over the square root of 2. But theta has to, not theta, it's not theta. Okay, it's phi. I don't know what my problem is today. Okay, anyway, phi has to stay between 0 and pi. That's always the restriction for phi, 0 to pi. And so the phi, the only place that happens between 0 and pi where the cosine is negative is at 3 pi over 4. So since you want the upper part, you're going to be between 0 and 3 pi over 4. So here is my r. This is x, this is y, this is z, and then my bounds on theta. And again, no restriction. Oh my goodness, I did it again. My bounds on my phi are 0 to 3 pi over 4. My bounds on my theta, 0 to 2 pi. So sorry, I don't know what my problem is. Okay, number 12. Let's try this one. Number 12. It's a cylinder between x squared plus z squared equals 4, and above the xy plane between the planes y equals -2 and y equals 2. So notice here's the picture. It's the top half of a cylinder, and then you cut off the left side and the right side at y equals 2 and -2. So here, because of the y issue, it kind of changes the cylindrical things a little bit. And so we're going to do something a little bit different. So if y was 0, then you would be see where this green thing is? That's where y is 0. You would have the half circle. It's this circle, but it's only the top half. in the XZ plane. So again, that's that green circle in the XZ plane. So if it's just two variables, then you can use polar, because polar is 2, cylindrical is 3. But now, because this is the XZ plane, now you're going to use Z's everywhere you would have used Y's in polar. So before you had X and Y in polar, now we're going to have X and Z, but it's still going to be polar. So that's a little confusing, but we're going to call it polar instead of cylindrical, because I don't want you to think that Z is Z, which it is in cylindrical, but not here. Here Z is playing the role of Y. And so X equals R cosine theta, and Z equals R sine theta. And then since X squared plus Z squared equals 4, we have R is 2, so we can substitute that in there and there. And so X becomes 2 cosine theta, Z is 2 sine theta. And then because it's the top half, we have between 0 and 2 pi. So this is a little bit weird, but think about it in the plane. So I'm gonna draw it over here. Think about it in the XZ plane. It's a little bit weird because we're used to thinking about phi that I've been calling theta. But this is what it is. Why is it 2 pi? It should be pi. 0 to pi. I apparently didn't check my answer. It should be 0 to pi. I'll fix it in a minute. I'll fix it in the notes when I scan them in and post them on Angel. But this is the picture. So it's the top half. It's this green circle, right? I don't know if you can see it good in my picture's kind of crazy with all the white out when I was trying to go back and make it dotted. But anyway, that should be 0 to pi. Okay, so now we need to account for the y. And so here, this is where it gets a little weird. This is the way the book does it, so I just did it this way so you can follow along with the book. I would have done this slightly differently, but there's really no good way to do it, so I figured this is maybe the lesser of two evils, I don't know. But to account for the y, what we're going to do is we're going to switch to u's and v's. So that's because everything up here was just theta, so it's a function of a single variable, but it didn't take into account the y. And so to take into account the y, you can let y be u. And then just because it makes more sense to have u's and v's instead of u's and thetas, we're going to change all of our thetas to v's. You don't really have to do that. You could leave them as thetas if you wanted to and have u's and thetas, but that's just kind of weird. So you should have u's and v's if you want it to be less weird. So here's your x, where I've just gone up here and replaced the theta with the v. Here's my y. Here's my z. Again, just replacing theta with a v. And then because y was between -2 and 2, what in the world? That's supposed to be a u. Hold on, I'm going to fix that because I'll forget about that. I'll remember to go back and fix the, well, let me write myself a note. Fix theta on number 12. Okay, anyway, I'm going to fix that here. So y is the same thing as u, and so u is between -2 and 2. And then theta, I need to fix that there too, is supposed to be between 0 and pi, and v is theta, so v should be between 0 and pi. So let me go ahead and fix that right now. That way you can see what it should look like. Hold on. So you can see everywhere it should be fixed. Ugh. Okay, sorry. I can't hold the paper. Okay, one more place. So I'm going to show you everywhere I'm fixing it. Okay, so up here, that should have been pi. And then here, and here, you can't see that one, and here. So 4 places I was fixing it in case you were copying my notes faster than I was getting to it. So here it should be 0 to pi, here it should be 0 to pi, here it should be 0 to pi, here it should be 0 to pi. Okay, sorry about that. I guess I was just looking at it in the first octant. In the first octant, it would be 0 to pi over 2. But there's the back side, back there, and so it goes all the way back like this to where x is -2, so it's 0 to pi, 0 to pi. Okay, so anyway, here's my r, and my u, and my v. Okay, so notice I have u's and v's here, and functions of u's and v's, and bounds on the u's and v's. Okay, hopefully that's my last crazy mistake. We'll see. Okay, so number 14, this one gets a little bit weirder. Here, because of the, you do have cylinders, and so you might think, hey, this is just like what we've been doing. But no, because of this plane is going to mess things up. It makes it a lot more complicated because of this plane. Because what you have is you have the part of the plane that's inside the cylinder. So you're not just looking at a cylinder anymore, you're looking at a plane that's inside of a cylinder, so it's a lot more complicated. So it's similar to number 12 in that we're going to use the polar stuff, but instead of starting with polar and thetas and then changing to the v's, we're just going to go straight to the v's. So here, instead of r and theta, I'm going to use u and v. So this is just like polar, like what I was doing in number 12, but I'm going to go ahead and go straight to the u's and v's because I'm going to have the same issue with the y, and I've got to take into account the y, so I'm just going to go straight to it this time. So x is u cosine v, z, because here, notice it's again the same issue, I don't have any y's, and so z is playing the role of y. So z is u sine v. And then this, if you graph this in the xz plane, this is r squared. So r would be the square root of 3. So this is what it looks like in the xz plane. It's the circle. Okay, so u is like the r, and so z is like the y. So this is like x squared plus y squared equals 3, which would be r squared. But now the z instead of y, but it's still going to be r squared. But u is like the r. So we have u's instead of r, so we've got u squared. So I don't know if that makes sense, but it's basically like here, this would have been r squared equals 3, but we're using u's instead of r's. So it's u squared equals 3, so u is the square root of 3. So my u is going to be between 0 and the square root of 3. And then the v is like the theta, no restriction here, so it's going to be between 0 and 2 pi. Now we have to find the y. So you go back up here to that, and you solve it for y. So this plane solved for y becomes this. And then you just substitute in for x and z. So I plug this in for x and this in for z, and that gives me my y. So here's my x, here's my y, here's my z, and then my bounds on u and v. So part B is similar, so you try it by yourself to see if this is making sense. So it's inside the cylinder, y squared plus z squared equals 2. So pause the video, try that by yourself. Okay, so notice here you have the YZ plane. So y is like x, z is like y. So y is u cosine v, z is u sine v. This is r squared, but r is the u, so it's really u squared. So u is the square root of 2. And so the plane, now you're going to solve it for x because you have to take into account the x because this is just y's and z's. So solving it for x, you get this. And then you substitute in for y and z. And so here's x, here's y, here's z. Again, this comes from the r, right? The values for the r is 0 to square root of 2. And then again, no restriction. V is like theta, so 0 to 2 pi. All right, so hopefully that makes sense. If that bothered you to not have the thetas first, you can do the thetas first. I don't know if that helps or not. But all right, so this picture is pretty bad. I don't know why I didn't even draw the 3D picture for number 14. Oh well, whatever. It would have looked very much like this. It's a cylinder and a plane, so it would have looked similar to this, but that plane was a lot harder to draw. So probably mentally that's why I just didn't even think to do it. But anyway, here this is the plane. And then this is the cylinder, so it's just the part of the plane that's inside the cylinder. So that picture I know is not great, but just gives you a rough idea of what's going on. So we're going to use polar again here, this time with x and y. So x and y are their normal selves this time. Oh, I forgot to tell you the directions changed here. We're actually doing the same thing, but the directions changed. 17 to 26, we're going to first find the parameterization, so that part of it's the same. But now we're going to use it to do the area. Okay, so start off the same way with the parameterization, but then keep going because we're going to find the integral in the area. Okay, so in polar, x is r cosine theta, y is r sine theta, z is negative x, and x is r cosine theta, so we have z as this. So here's my parameterization, x, y, z. My r is between 0 and 2 because of this. This is r squared is 4, so r is 2. And then no restriction on the theta, so theta is between 0 and 2 pi. So here's my formula for, why did I write that twice? Oh, I see, because the formula is normally in u's and v's. I rewrote it in r's and thetas. So I need the derivative. So it's the derivative of this r, first with respect to r and then with respect to theta. So take the derivative with respect to r and you get this. Take the derivative with respect to theta and you get this. And then you're going to do the cross product. So top row is ijk, second row is r sub r, Third row, r sub theta. Do your cross product. This is like, it took several lines to fit this. This is the I, the J, and then the K. So all of this is together one thing. And then it simplifies a little bit more to this. And then because of the sine squared and cosine squared, like here you can factor out the r. Sine squared plus cosine squared is 1. Here, these are the same thing, but one's positive and one's negative, so they're just 0. Here again, factor out the r, and cosine squared plus sine squared is 1. So it simplifies down to this. And then we want the magnitude. So we do the magnitude, and that becomes this. So this is actually the function that we're going to integrate. So I have my bounds from here. There's my bounds. I have my function here. And so this is what I'm integrating. And so here's my function, here's my bounds. dr and d theta are like u and v. Here's those are my parameters. So integrate, simplify, and you get 4 pi square root of 2. All right, so you try number 20 by yourself. It's the same kind of idea as what we were doing before. So try number 20. Pause the video and try it by yourself. Okay, so here we're going to use polar again. Well, actually, this is cylindrical, but whatever. So x squared plus y squared is r squared. So z is r over 3. And then here's some values for z that I'm going to use to find my r. So z is 1 and z is r over 3. So r is 3. If z is 4/3, r is 4. So r is between 3 and 4. Theta is between 0 and 2 pi. So again, because no restrictions on the theta. So here's my r, here's the x, here's the y, here's the z. I need both of the derivatives. Here's the partial with respect to r, here's the partial with respect to theta. Set it up in for the cross product in the 3 by 3 determinant. Do the cross product, and so this is my cross product. Then I'm going to do the magnitude. So factor out the 1/9 r squared, cosine squared plus sine squared is 1, add those together. And so this is my magnitude. Okay, so I had my bounds on the previous page. Here's my function I just found here. dr d theta, integrate, and you should get 7 square roots of 10 pi over 3. All right, so now one more. I'll have you, I don't know why I did so many of these. I'll let you try this one by yourself. I'm not going to walk through this one quite as much. This one is pretty much the same. So try 22 by yourself. Okay, so here it's one of those things that I'm going to use polar and start with thetas, but switch to u's and v's kind of a situation. So this is r squared, so r is square root of 10. This is in polar. I'm going to switch to u's and v's. And so here's my x, and here's my z. My y is going to be the u. Here's my bounds. So there's my r. And then I'm going to find the derivatives, cross product, magnitude, integral. Answer should be 4 pi square root of 10. Okay, so just in case I went through that too fast, if you missed anything, you can pause it at any point. See if you can figure out where you went wrong. Okay, but now let's look at something different. So those were all kind of the same. Let's look at something different. Now we're going to look at this formula for what do we do if we can't find the parameterization. So if we can't find the parameterization, we're obviously going to use a different formula. So here we have the area of the band cut from this paraboloid by the planes z equals 2 and z equals 6. So the paraboloid, it originally started down here at the origin, and then it opened up. That's the way the paraboloid did. But I cut it off at z equals 2 on the bottom, and I cut it off at z equals 6 on the top, so it's just this little section of it here. Okay, so here was my thing they gave me. This was the paraboloid. And in this one, I have a capital F, and the capital F is a function of x, y, and z that's equal to c. So here's the function of x, y, and z. Here's the c. So the F is that function. And now I need the gradient of it. So the gradient, remember, is just the vector of all the partial derivatives. So find the 3 partial derivatives of this. So my gradient vector is here. And then I need the magnitude of my gradient vector. So find the magnitude, and I get this. Okay. Now I need the p. Okay, so r, hold on, go back to my picture. R is the shadow. See it at the bottom, the shadow? And so the shadow is 2-dimensional, and it's in the xy plane. So it is in the xy plane, so the vector k would be normal to the xy plane, and it's also a unit vector, so that's going to be my p. So I'm going to use k for my p, so k in component form 0, 0, 1. And then here was my gradient vector, so the dot product between those two gives me -1. And then for the bounds, I'm going to switch this to polar. So here it is not in polar. This is what it was originally. Sorry, I had to skip back. That's why the video got shaky right there for just a second. Anyway, here it is in not polar. This is in regular rectangular. And so this was the magnitude of the gradient vector. This is the absolute value of the dot product. But now I'm going to change it to polar. So it was in rectangular. When I change it to polar, the dA has to become r d theta. Factor out the 4, x squared plus y squared is r squared. Absolute value of -1 is 1. And then in polar, going back here to this shadowy picture, the z was between 2 and 6. And z is r squared. So z is the same thing as r squared, and z is between 2 and 6. Then r squared is between 2 and 6, so r is between the square root of 2 and the square root of 6. So that's my bounds on the r. No restriction on the theta, so 0 to 2 pi. So this would be my integral. I can do a u substitution. And so the r's will cancel. Leaves me with this. Integrate. Plug back in for u. Here's my bounds. So plugging in. So here we have square root of 6 squared is 6. Times 4 is 24 plus 1 is 25. Square root of 2 squared is 2 times 4 is 8 plus 1 is 9. And then 25 to the 3/2 power, you take the square root first, so that would be 5, and then you cube it, which is 125. For the 9, square root first is 3, 3 cubed is 27, so it simplifies, the 98 times the 112 simplifies down to this. Integrate with respect to theta, and you get 49 pi over 3. All right, so you try this next one by yourself. This is the last one. This is number 46. So find the area of the surface cut from this, which is another paraboloid, by the plane y equals 0. Okay, so pause the video, try that by yourself. Okay, so here's the picture. It's a paraboloid. It's here at 2 on the y-axis opening this way, but I cut it off at y equals 0, which is the xz plane. So this equals 2, that's the f equals c. Why do I have equals 0? That's supposed to be a c. Hold on, let's fix that. C. Okay, and so this is my function. So I find the gradient, take the derivatives. There's my gradient vector, magnitude. Now r is in the xz plane. R is that shadow part, so that's the shaded part. It's in the xz plane, so I'm going to let the p be j. P be j, like peanut butter and jelly. I'm going to let the p vector be the j vector. So I'm going to do the cross product here, and that ends up just being 1. And then here's what I have. The magnitude of the gradient vector over the absolute value of the dot product. I'm going to again change that to polar. So here this circle, the circle is where y equals 0. So if y equals 0, then this becomes this. And so I have, well, I didn't show that work, but that would be r squared equals 2. So r would be the square root of 2. Oh, I didn't show that work. And then theta is between 0 and 2 pi. So this was r squared equals 2. So r is the square root of 2. So r is between 0 and the square root of 2. And then notice what happens. Different bounds, but see how this is exactly what we just did in number, whatever number was before this, 38. See how that's the same as in 38? Oh, I wrote it right there. I guess it would have helped if I left this paper. Anyway, same thing, different bounds. So it's going to give you the same integral, but then you're plugging in different numbers. And so it simplifies down to just this. So we're going to do more of this in 15.6. So you'll get more practice with it there. But hopefully this is enough for you to make sense of it in 15.5. So if you have any questions, send me an email.